I'm going to give a quick tutorial on how to do 2D interpolation using EngineeringPaper.xyz and also how to make response surfaces. Now, for many mechanical engineers, when you think of 2D interpolation, you're thinking of the steam tables in the back of the thermo book and doing interpolations by hand. Fortunately, with Engineering Paper, with the recent cool prop integration, we already have steam tables and humid air and dry air properties amongst many other fluids, so you don't have to do that. But if you're faced with other 2D tabular data, which often occurs in like engineering standards and things like that, where you have to do interpolation on two axes, this will show you how to do that. So here I've done a design study. So I have a panel, and in SOLIDWORKS I've done a design study where I vary the rib height and the material thickness. It's a plastic panel. Apply a force and output the displacement and the mass. And here I've put the tables in a form that you'd often see in like an engineering standard, just to kind of show you how to format that data to work with the 2D interpolation. So here we have displacement with rib height and thickness, and along two axes, and in all the displacements and masses in these individual cells. If you're interested in seeing a tutorial on how to do a design study in SOLIDWORKS, I'm not going to cover that here, but if you're interested in that video, just put in the comments. If there's enough interest, I'll make a video on that in the future. All right, so you have to format this data correctly. So from the engineering standard, it might look like something like this, like a 2D grid. What engineering paper is going to want is it in columns, which each column for an input and each column for an output, so in individual columns. So here I have thickness, height, displacement, mass. Basically what it's doing is taking this data, kind of unwrapping it and putting it in columns. So for example, all the 2.5 height displacement data is right here in a column, and then going down to the 5 is the next set of 3 values, and then this row is the final 3 values. Just kind of unwrapping it, put it in the column. So it's all the entries with the inputs and outputs, and also the same thing for this mass table. This is the kind of the format that engineering paper is going to want, and it's going to be easiest to put this data into Excel and format it the way engineering paper wants it. You can put your variable names in the top row, and if you want, in the second row, you can put the units, put those in square brackets, and engineering paper will try to detect those. Once you have those files, you can actually insert a data table cell and click the import spreadsheet button, or you can just drag and drop the spreadsheet right on your engineering paper page, and it'll automatically add a data table for you. So now we have this data in engineering paper, so it's that same data that's in these two tables. I have the variable names, and if there's any errors, it'll highlight it in the red where you need to fix it to make it conform kind of the engineering paper variable names. And then I have the units that also will give you errors if there's any errors with the units. Everything's coming through clean here. And now, so what I want to do is do the interpolation. So what I'm going to do is, I'll show you two ways. We're going to do a interpolation first, because that's how you'd probably mostly, if you're doing bilinear interpolation or a two-axis interpolation on standards data, that's how you'd probably do it, kind of match how you do it by hand. So let's do that first. So I'm going to add interpolation. By default, it's doing one-axis interpolation, but I want to do two axes, so I'll do 2. And then you indicate which columns are the inputs and which columns are the outputs, okay? So here I'm going to do an interpolation function for displacement. So I want that to be my output column. I want my first input to be thickness, my second input to be height, and I could swap those if I wanted. So the other thing I'm seeing here, it's giving me this little icon, and that little grid icon. It's telling me it's detected this as grid data. And when it does that, it's going to use bilinear interpolation just like you do by hand. It's just a little more accurate if the data fits this format. So it says 2D grid data detected using bilinear interpolation. What it's looking for here is it's basically looking for a full factorial where all possible combinations are included. So here, this grid fits naturally with that. If I were to change one of these values slightly, let's say do 2 point, just add a little bit of difference there, it's no longer detecting it as grid data. So it is important that the X and Y values kind of match this grid exactly for it to detect that. If you're not grid data, it'll just use a triangulation of the data. It'll still do interpolation. Not going to be quite as accurate as if it's a grid, but if you have non-structured data, it can still interpolate it. But if it's structured data like we have here on 2D grid, you definitely want to make sure that that 2D thing shows up. If I was missing a row by accident, that would disappear as well. Or if I had repeated data, it's going to detect that. It's going to help you detect errors. So if you have 2D grid data, make sure this is showing up. If some of these cells are missing, sometimes standards don't have data in every grid, it'll just fall back to the triangulation of the data instead. Just be aware of that. All right, and so I need to name this. By default, it gives the interpolation 1 name. I'm going to give it a little more informative name. I'm going to call it displacement since that's the output. Now, this column is already going to be the variable displacement, so I need to change this. I'm going to change it to a capital D just to make it a different name. Otherwise, if I did a lowercase d, it will give me a warning that I have a duplicate variable name. And I can add a number at the end, just change the name in some way. So now I have this function. I can use it just like I use any function in a mathematical formula. Keep in mind that the first input, it has to be thickness, second one's mass. It's going to use the units I have here. So it's unit aware. It's going to check that, give me errors if I'm not using the units. So let's check the displacement. I need to be within these ranges so I'm not extrapolating. So let's check the displacement at like 3 thickness and let's say like 10 rib height. So if I do displacement, let's type that function name. My first entry is going to be my displacement. I do need to put units on that, or the material thickness. The second one's going to be the rib height, let's say 10 millimeters. So this is a case, this is an entry that isn't in my table, and I hit equals to evaluate that. So it's going to default to meters. I could either change my sheet default units. Let's change that actually. We'll just switch to millimeters here. So it defaults to millimeters. But if I wanted this to be in inches, it'll work the same way as anything in engineering paper. All right, so I got 12 millimeters displacement. So it's done that interpolation just the same way if I did bilinear interpolation to get that value. I can also plot with that. So let's say I want to look at all the displacements for a rib height of 11 across the range of displacement. So I can add a plot here. All right, so I'm going to do a parametric plot here. So do a parametric plot, I give it a pair of x and y values. So x we'll define in a second here. And I'm going to call the displacement function for the y values. And so displacement, my x is going to be my thickness. I need to give it, I'm going to use a rib height that's kind of in the middle of my range. I'm going to use 11, so I'm grabbing that row of data. So we'll do 11. I need to put units here. Otherwise, it's not going to work correctly. And then I'm going to say 4, and then give my x range. Okay, so I'm going to say, now I could just do 2.5 to 7.5, but if this data were to change, I want to kind of follow the min and the max. So I'm going to use min. This thickness will become a vector that I can use. I'm going to use the min function and the max function. So min thickness less than equal to x, less than equal to max thickness. All right, and so if I hit equals, it's going to create that curve. You see it's doing a linear interpolation. Now these values that, it should go right through those values in my table, and I'll plot those points in a second. But before I do that, I want to show you that I can also do, normally for a DOE or design of experience, you wouldn't do a linear interpolation. I just want to show you that since you'd use that for like a standards type data. For a DOE, you more frequently use what's called a response surface or a polynomial fit. So let's add that, and we can just keep adding different fits to this data. So for this is going to fit a polynomial, a least squares fit rather than an interpolation. And so I'm going to do inputs of 2, and I want to do, usually for this type of data, you do a second order polynomial so you capture any nonlinearity. And I'm just going to leave that as polyfit 1 because it's got to have a different name. So I'll just polyfit 1 will work for this data. And so I can do the same thing I did here. So I can call that function in the same way. So if I add a math cell, so I can just hit enter to add a math cell, and I'll do call polyfit 1 as a function, and we'll call it the same point. It'll probably be a little different because it's a polynomial fit. We'll compare it in the graph below. Let's do that same fit as a polynomial least squares fit rather than an interpolation fit. Now it's saying it doesn't find it, that's because I forgot the 1 here. So it couldn't identify that function. So it's pretty close, but a little different, right? And let's plot it to see the difference in the plot. So I can hit here, do enter. This one I also want to do, let's just copy it because it's mostly going to be the same. Control C, Control V. The only thing different is I'm going to use polyfit instead of displacement. All right, so we're going to see that polynomial fit. You see it's a curved line. The other thing is with the polynomial fit, it's not going to go through those points, right? We're doing a best fit least squares approximation. We can do higher order, but usually use a second order for this type of thing. So it's just a fit to that data. Finally, here I'll add, we'll add one more row. I'm going to add the actual data for when the rib height is 11, just to compare that. So 2.5, 5, and 7.5. So I can actually do a scatter plot here. Easiest way to do scatter plots is put a couple vectors in here. So 3 by 1 vector, comma, 3 by 1. That'll do my x and y values. And I just say equals here, but I need to enter the numbers in here. So if my x values are going to be, let's see, there's 2.5, 5, and 7.5. 2.5. tab 5 and 7.5. Keep in mind I do need to put units on this. I'll just multiply by the 1 millimeter to add units. And then I need to do the rib height, the displacement for those values. So find these in the table and copy them. So let's do the 2.5 at 11 is this value. So I'll put that in here. I'm just doing this so we can see where the original points were. The 5 at 11 is this value. I'll paste that. And then 7.5 at 11 is this value. Normally you wouldn't do this, but I just want to show where those values come in here. Time, again, I need to add units, otherwise it's not going to plot it on the same axes. All right, so now we see the points. We can see the interpolation function goes right through those points as we expect, just like a bilinear interpolation would if you did it by hand. And then our response surface is an approximation of best fit curve. That's just a slice through the height of 11. I could do other y values here as well. One thing I want to show you is the one important difference between interpolation and polyfit is how it handles extrapolation. So here I've picked a point that is not extrapolating, but let's say I change this x value to 8. That's clearly outside my data. So if I'm doing this interpolation, it gives me an error. Okay, so interpolation is not going to let you extrapolate. Another reason you might want to use it with that kind of standards data, so you're making sure you're not going outside of your normal data. So put that back, so get rid of that error. But on a polyfit, it's going to happily let me extrapolate. So like on a response surface, it's going to let me go beyond my original data. And so I just want to point out that kind of difference between the interpolation and the polyfit. But this is to show you how to use bilinear interpolation and multi-input polynomial fits for a response surface in EngineeringPaper.xyz. Put any questions you might have in the comments, share, like to kind of spread awareness of EngineeringPaper.xyz.